Question 1. Stakeholder feedback indicates a noticeable increase in odors emanating from the pre-aeration basins at the wastewater treatment plant. As the certified operator, you suspect this may be related to the effectiveness of grease and oil removal or the efficiency of the aeration process itself. What is the most appropriate initial course of action to address this situation? Option A. Conduct a thorough operational assessment of the pre-aeration basin, including checking aeration equipment performance, grease and oil removal mechanisms, and influent characteristics to identify the root cause of the increased odor. Option B. Inform the stakeholders that odor fluctuations are normal during certain weather conditions and no immediate action is required. Option C. Immediately increase the dosage of odor-masking chemicals in the pre-aeration basins to suppress the smell until a more permanent solution can be found. Option D. Reduce the aeration rate in the basins to conserve energy and see if that alleviates the odor issue. The correct answer is A. Conduct a thorough operational assessment of the pre-aeration basins, including checking aeration equipment performance, grease and oil removal mechanisms, and influent characteristics to identify the root cause of the increased odor. Explanation. This scenario presents a common operational challenge where public perception and potential environmental impact intersect. The professional challenge lies in balancing the immediate need to address odor complaints with the long-term operational efficiency and regulatory compliance of the pre-aeration system. A hasty or incomplete response could lead to ineffective odor control, increased operational costs, or even regulatory violations. Careful judgment is required to identify the root cause of the increased odor and implement a sustainable solution. The correct approach involves a systematic investigation of the pre-aeration basin's performance, focusing on factors that influence grease and oil removal and overall aeration efficiency. This includes verifying the operational parameters of the aeration equipment, assessing the effectiveness of grease and oil removal mechanisms, and potentially adjusting chemical dosages or operational schedules. This methodical approach ensures that the implemented solution directly addresses the underlying cause of the odor, aligning with regulatory requirements for odor management and wastewater treatment plant performance. Specifically, regulations often mandate that treatment processes achieve a certain level of pollutant removal and that nuisance conditions like excessive odor are minimized. An incorrect approach would be to solely focus on masking the odor with chemicals without investigating the root cause. This fails to address the underlying issue of potentially inefficient grease and oil removal or inadequate aeration, which are critical functions of the pre-aeration stage. Such an approach is likely to be a temporary fix, potentially leading to recurring odor problems and increased chemical costs, and may not meet regulatory standards for effective treatment. Another incorrect approach would be to immediately shut down or significantly alter the aeration process to reduce airflow. While this might temporarily reduce energy consumption, it would likely compromise the effectiveness of grease and oil separation and the biological processes occurring in the basin, potentially leading to worse effluent quality and increased odor in the long run. This deviates from the operational requirements for effective pre-aeration and odor control. Finally, an incorrect approach would be to dismiss the stakeholder feedback as non-critical without any investigation. This demonstrates a failure to engage with the community and a disregard for potential operational issues that could be impacting the surrounding environment. Regulatory frameworks often include provisions for public engagement and require operators to address nuisance conditions. The professional reasoning process for this situation should involve 1. Acknowledging and documenting stakeholder concerns. 2. Initiating a diagnostic process to identify the root cause of the increased odor, focusing on the pre-aeration system's performance regarding grease/oil removal and aeration. 3. Evaluating potential solutions based on their effectiveness, cost efficiency, and regulatory compliance. 4. Implementing the chosen solution and monitoring its performance. 5. Communicating the actions taken and the results to stakeholders. Question 2. The risk matrix shows a high probability of chemical exposure and potential for unexpected equipment startup during routine maintenance of the aeration basin chemical feed system. As the lead operator, what is the most appropriate course of action to ensure worker safety and regulatory compliance? Option A. Proceed with maintenance after reviewing the general chemical safety guidelines and ensuring basic PPE like gloves and eye protection are worn, assuming the system is not actively pumping chemicals. Option B. Post a warning sign near the chemical feed system indicating potential hazards and instruct workers to be cautious while performing maintenance. Option C. Conduct a thorough job hazard analysis, JHA. Consult the specific safety data sheet, SDS, for the chemicals involved. Implement lockout/tagout, LODO procedures to de-energize the system, and ensure all required PPE, including respiratory protection if indicated by the SDS, is used. Option D. Rely on the experience of the maintenance crew to identify potential hazards and perform the work efficiently, with minimal disruption to operations. Correct answer is A. Proceed with maintenance after reviewing the general chemical safety guidelines and ensuring basic PPE like gloves and eye protection are worn, assuming the system is not actively pumping chemicals. Explanation. The risk matrix shows a high probability of chemical exposure during routine maintenance of the aeration basin chemical feed system. This scenario is professionally challenging because it involves multiple safety protocols that must be integrated and rigorously followed to prevent serious injury or fatality. The operator must not only understand the hazards of the specific chemicals, but also the procedures for safe handling, the necessity of appropriate personal protective equipment, PPE, and the critical steps of lockout/tagout, LODO, to de-energize equipment before entry or maintenance. A failure in any one of these areas can have severe consequences. The correct approach involves a comprehensive safety assessment and adherence to all applicable regulations. This includes conducting a thorough job hazard analysis, JHA, for the specific task, ensuring all necessary PPE, e.g., chemical-resistant gloves, eye protection, respiratory protection if indicated by the safety data sheet, SDS, is available and properly used, verifying that the chemical feed system is properly isolated and de-energized using LODO procedures as per OSHA lockout/tagout standard, 29 CFR 1910, 147, and consulting the SDS for detailed chemical handling and emergency response information. This approach is mandated by federal regulations such as OSHA Hazard Communication Standard, 29 CFR 1910, 1200, and Confined Space Entry Standard, 29 CFR 1910, 146, and it reflects a commitment to worker safety and regulatory compliance. An incorrect approach that relies solely on general knowledge of chemical handling, without verifying specific SDS information or implementing LODO procedures, is a significant regulatory failure. The Hazard Communication Standard requires employers to inform employees about chemical hazards and provide training, which includes understanding SDSs. Neglecting to consult the SDS for specific PPE requirements or emergency procedures violates this standard. Similarly, failing to implement LODO procedures before working on energized equipment is a direct violation of 29 CFR 1910, 147, which is designed to prevent unexpected startup of machinery, a leading cause of industrial injuries. Another incorrect approach that involves entering the aeration basin without proper atmospheric testing and attendant presence, even if the chemical feed system itself is isolated, fails to comply with the Confined Space Entry Standard. This standard mandates a rigorous permit-required confined space entry program, including atmospheric monitoring, ventilation, and rescue plans, to protect workers from atmospheric hazards and engulfment. Professional decision-making in such situations requires a systematic approach. First, identify the task and its associated hazards. Second, consult all relevant regulatory requirements and company safety procedures. Third, conduct a JHA to detail specific steps and required safety measures. Fourth, ensure all personnel are trained and equipped with the correct PPE. Fifth, implement all necessary control measures, including LODO and confined space entry protocols. And finally, document all safety procedures and training. This structured process ensures that all potential risks are identified and mitigated according to established safety principles and regulatory mandates. Question 3. Regulatory review indicates that a wastewater treatment plant operator has observed a significant and uncharacteristic increase in the influent biochemical oxygen demand, BOD, and suspended solids concentration. The operator must decide on the immediate course of action to ensure compliance with the facility's National Pollutant Discharge Elimination System, NPDES, permit. Which of the following approaches best aligns with regulatory requirements and professional operator responsibilities? Option A. Initiate a comprehensive data collection and analysis of the influent characteristics. Consult the facility's NPDES permit and SOPs for guidance on handling such variations, and implement process adjustments or notification procedures as dictated by regulatory requirements and facility protocols. Option B. Continue normal operations, assuming the influent variation is temporary and will self-correct, while monitoring effluent quality closely. Option C. Contact the nearest neighboring treatment plant operator to ask for their advice on how they typically handle high BOD and suspended solids influent. Option D. Immediately adjust the aeration basin dissolved oxygen levels and sludge wasting rates based on a general understanding of high BOD influent, without further investigation or consultation of permit limits. The correct answer is D. Immediately adjust the aeration basin dissolved oxygen levels and sludge wasting rates based on a general understanding of high BOD influent, without further investigation or consultation of permit limits. Explanation. Scenario analysis. This scenario presents a common challenge for wastewater treatment plant operators, balancing operational efficiency with regulatory compliance when faced with unexpected influent characteristics. The challenge lies in making a timely and effective decision that protects public health and the environment while adhering to established treatment standards and permit limitations. Operators must exercise sound judgment, drawing upon their technical knowledge and understanding of the regulatory framework. Correct approach analysis. The correct approach involves a systematic, data-driven decision-making process that prioritizes regulatory compliance and environmental protection. This begins with immediate data collection and analysis to understand the nature and extent of the influent deviation. Based on this analysis, the operator must consult the facility's operating permits, standard operating procedures, SOP, and relevant regulatory guidelines to determine the appropriate response. This might involve adjusting treatment process parameters, initiating emergency response protocols, or notifying regulatory agencies as required. The justification for this approach is rooted in the fundamental responsibility of a certified operator to ensure that the wastewater treatment plant operates within its permitted limits and effectively treats wastewater to prevent pollution. This aligns with the core principles of public health protection and environmental stewardship mandated by regulatory bodies. Incorrect approaches analysis. Ignoring the influent deviation and continuing normal operations represents a significant regulatory and ethical failure. This approach disregards the potential for treatment process upset, which could lead to the discharge of inadequately treated effluent, violating permit limits and posing a risk to receiving waters and public health. It demonstrates a lack of diligence and a failure to uphold the operator's professional responsibility. Implementing drastic, unverified process changes without understanding the root cause of the influent deviation is also a flawed approach. While proactive, this can lead to unintended consequences, potentially destabilizing the treatment process further or causing new compliance issues. It bypasses the critical step of data analysis and informed decision-making, which is essential for effective problem-solving and regulatory adherence. Relying solely on anecdotal experience or the advice of less experienced personnel without cross-referencing with official documentation and regulatory requirements is another ethically and regulatorily unsound practice. While experience is valuable, it must be grounded in and validated by the established regulatory framework and facility-specific procedures. This approach risks making decisions based on incomplete or inaccurate information, potentially leading to non-compliance. Professional reasoning. Certified wastewater treatment plant operators must employ a structured decision-making framework when faced with operational challenges. This framework should include 1. Situation assessment. Promptly identify and quantify the deviation from normal operating conditions. 2. Information gathering. Collect relevant data including influent characteristics, process performance indicators, and historical data. 3. Regulatory review. Consult the facility's operating permit, relevant state and federal regulations, e.g., Clean Water Act NPDES permit requirements, facility SOPs. 4. Impact analysis. Evaluate the potential impact of the deviation on treatment processes and effluent quality. 5. Action planning. Develop and implement a corrective action plan based on the assessment and regulatory requirements. 6. Documentation and reporting. Maintain detailed records of the event, actions taken, and communicate with regulatory agencies as necessary. This systematic approach ensures that decisions are informed, compliant, and protective of public health and the environment. Question 4. The audit findings indicate a consistent increase in effluent turbidity and a slight elevation in total suspended solids, TSS, over the past month, alongside a noted decrease in dissolved oxygen levels within the secondary clarifier. What is the most appropriate initial response to these findings? Option A. Immediately increase the dosage of polymer in the primary clarifier to improve settling of incoming solids. Option B. Recommend a significant increase in aeration rates for the entire plant to address the low dissolved oxygen. Option C. Assume the issue is solely related to influent characteristics and adjust the primary treatment processes accordingly without further investigation. Option D. Conduct a thorough investigation into the performance of the secondary biological treatment process and the sludge settling characteristics in the clarifier to identify potential causes for the increased solids and reduced dissolved oxygen. The correct answer is D. Conduct a thorough investigation into the performance of the secondary biological treatment process and the sludge settling characteristics in the clarifier to identify potential causes for the increased solids and reduced dissolved oxygen. Explanation. This scenario presents a professional challenge because it requires an operator to interpret audit findings related to wastewater characteristics and determine the most appropriate corrective action without resorting to immediate, potentially costly, or unnecessary interventions. The challenge lies in understanding the interplay between physical, chemical, and biological parameters and their impact on treatment efficacy, while adhering to regulatory compliance and operational efficiency. Careful judgment is required to differentiate between minor fluctuations and significant deviations that necessitate specific actions. The correct approach involves a systematic evaluation of the audit findings, focusing on identifying the root cause of any indicated deviations in wastewater characteristics. This approach prioritizes understanding the why behind the observed data before implementing solutions. For example, if the audit highlights elevated BOD, the correct response would be to investigate potential sources of increased organic loading or issues with biological treatment processes, rather than immediately increasing chemical dosing without understanding the cause. This aligns with regulatory requirements for effective wastewater treatment and operational best practices, which mandate a data-driven, problem-solving methodology. It ensures that resources are used efficiently and that the corrective actions directly address the underlying issues, leading to sustained compliance and optimal plant performance. An incorrect approach would be to immediately implement a broad, unspecific corrective action, such as significantly increasing chemical coagulant dosage, without a thorough investigation into the specific wastewater characteristics identified in the audit. This fails to address the potential root cause, which might be biological rather than chemical. It also risks overtreating the wastewater, leading to unnecessary chemical consumption, increased sludge production, and potential impacts on downstream processes or effluent quality, thereby violating principles of efficient and effective operation. Another incorrect approach would be to dismiss the audit findings as insignificant without proper analysis. This is a direct failure to comply with regulatory oversight and internal quality control procedures, potentially leading to noncompliance with effluent standards and a decline in treatment performance. Ignoring the data prevents proactive problem solving and can result in more severe issues later. Professional reasoning in such situations should follow a structured decision-making process. 1. Thoroughly review and understand all audit findings, noting specific parameters and their deviations. 2. Correlate these findings with current operational data and historical trends. 3. Formulate hypotheses regarding the root causes of the deviations, considering physical, chemical, and biological factors. 4. Prioritize investigations based on the potential impact on treatment efficacy and regulatory compliance. 5. Develop and implement targeted corrective actions based on the identified root causes. 6. Monitor the effectiveness of the implemented actions and adjust as necessary. This systematic approach ensures that decisions are informed, compliant, and contribute to the overall operational integrity of the wastewater treatment plant. Question 5. Compliance review shows that during a routine inspection, the wastewater treatment plant operator noticed a warning light indicating a potential issue with the primary bar screen's automated raking mechanism. The operator is concerned that stopping the screen for immediate investigation might cause a temporary backup of influence. What is the most appropriate course of action for the operator to take? Option A. Temporarily disable the warning light system to avoid unnecessary alarms and continue operating the bar screen as normal until a scheduled maintenance period. Option B. Attempt to manually override the warning light and adjust the raking mechanism without consulting the supervisor or SOPs, hoping to resolve the issue discreetly. Option C. Immediately report the warning light to the supervisor and consult the plant's standard operating procedures, SOP, for guidance on addressing equipment malfunctions, even if it means a temporary reduction in screening efficiency or a brief operational pause. Option D. Continue operating the bar screen without addressing the warning light, assuming it is a minor glitch that will resolve itself, and only investigate if a significant operational problem arises. The correct answer is C. Immediately report the warning light to the supervisor and consult the plant's standard operating procedures, SOP, for guidance on addressing equipment malfunctions, even if it means a temporary reduction in screening efficiency or a brief operational pause. Explanation: this scenario presents a professional challenge because it involves a conflict between immediate operational expediency and long-term regulatory compliance and environmental protection. The plant operator is faced with a situation where a minor, seemingly insignificant deviation from standard operating procedures could lead to more significant problems if not addressed correctly. The ethical dilemma lies in balancing the pressure to maintain continuous operation with the responsibility to adhere to established protocols designed to protect public health and the environment. Careful judgment is required to assess the potential risks associated with each course of action. The correct approach involves immediately reporting the issue and following established protocols for addressing equipment malfunction or deviation from standard operating procedures. This aligns with the fundamental principles of responsible wastewater treatment plant operation, which prioritize safety, compliance, and environmental stewardship. Specifically, regulatory frameworks for wastewater treatment plants, such as those outlined by the U.S. Environmental Protection Agency, EPA, under the Clean Water Act and relevant state-level regulations, mandate that operators maintain equipment in good working order and report any deviations that could impact treatment efficacy or permit compliance. The ethical obligation of an operator is to act in the best interest of the public and the environment, which includes proactive problem-solving and transparent communication with regulatory bodies and supervisors. An incorrect approach would be to attempt to bypass or temporarily disable a safety feature on the bar screen without proper authorization or a clear understanding of the long-term consequences. This action directly violates regulatory requirements for equipment maintenance and operational integrity. It also poses an ethical failure by circumventing established safety and operational protocols, potentially leading to increased debris bypass into downstream treatment processes, which could compromise treatment efficiency and violate discharge permit limits. Furthermore, it demonstrates a lack of due diligence and a disregard for the established procedures designed to prevent such issues. Another incorrect approach would be to ignore the warning light and continue operating the bar screen as if no issue exists. This is a clear abdication of the operator's responsibility to monitor and maintain equipment. Regulatory frameworks universally require operators to be vigilant in their oversight of plant operations. Ignoring a warning signal is not only a failure to comply with operational standards, but also an ethical lapse, as it prioritizes convenience over the potential for environmental damage and permit violations. This approach creates a significant risk of equipment failure and untreated wastewater discharge. A third incorrect approach would be to only address the warning light when it becomes a critical operational failure, rather than proactively investigating the cause. While this might seem like a reactive solution, it is insufficient from a regulatory and ethical standpoint. Proactive maintenance and troubleshooting are essential components of responsible plant operation. Waiting for a critical failure can lead to more extensive damage, longer downtime, and a higher likelihood of permit violations. Ethically, operators are expected to be diligent and preventative in their approach to managing plant operations, rather than solely reactive. A professional decision-making process for similar situations should involve a systematic approach. 1. Recognize and acknowledge the deviation or warning signal. 2. Consult relevant operating manuals and standard operating procedures, SOP. 3. Assess the immediate risk to plant operations, personnel, and the environment. 4. Communicate the issue to supervisors and relevant personnel. 5. Follow established protocols for troubleshooting, repair, or temporary measures, ensuring all actions are documented. 6. If necessary, consult with regulatory agencies or seek expert advice. 7. Prioritize actions that ensure compliance with permits and protect public health and the environment. Question 6. The monitoring system demonstrates that the concentration of a specific pollutant in the treated effluent is consistently trending upwards and has recently exceeded the daily average limit specified in the facility's NPDES permit, although it has not yet reached the maximum daily limit. Which of the following actions best reflects the operator's immediate responsibility under federal and state wastewater regulations? Option A. Immediately initiate corrective actions to bring the pollutant concentration back below the daily average limit and consult the NPDES permit for specific reporting requirements related to this exceedance. Option B. Adjust the reporting of the monitoring data to reflect a value below the daily average limit to avoid triggering any immediate regulatory scrutiny. Option C. Continue normal operations and monitor the pollutant concentration, as it has not yet reached the maximum daily limit, assuming the trend will self-correct. Option D. Immediately notify the state environmental agency of a permit violation, even though the maximum daily limit has not been breached, and await further instructions. The correct answer is A. Immediately initiate corrective actions to bring the pollutant concentration back below the daily average limit and consult the NPDES permit for specific reporting requirements related to this exceedance. Explanation. This scenario presents a common challenge for wastewater treatment plant operators, interpreting monitoring data in the context of complex regulatory requirements. The professional challenge lies in accurately assessing compliance, identifying potential violations, and taking appropriate corrective actions to protect public health and the environment, all while adhering to the strict mandates of the Clean Water Act and associated state and local regulations. Failure to correctly interpret data or respond to deviations can lead to significant environmental damage, legal penalties, and reputational harm. The correct approach involves a thorough understanding of the facility's National Pollutant Discharge Elimination System, NPDES, permit, including its specific effluent limitations and monitoring frequencies. When the monitoring system indicates a parameter is approaching or exceeding an effluent limitation, the operator must immediately consult the permit to determine the reporting thresholds and required actions. This includes understanding the difference between a monitoring exceedance that requires notification and a permit violation that necessitates corrective action plans, and reporting to the regulatory agency. The ethical and regulatory justification for this approach is rooted in the operator's duty to operate the plant in a manner that prevents pollution and ensures compliance with federal and state laws, as mandated by the Clean Water Act. An incorrect approach would be to disregard the data if it is only slightly above a historical average but not yet at a permit limit. This is a regulatory failure because it ignores potential trends that could lead to a future violation and fails to proactively manage the treatment process. Another incorrect approach is to assume that a single exceedance automatically constitutes a permit violation, requiring immediate public reporting, without first consulting the specific terms of the NPDES permit. This is a procedural and regulatory failure, as permits often define different thresholds for notification versus violation, and immediate, unsubstantiated reporting can lead to unnecessary alarm and administrative burdens. Finally, an incorrect approach is to delay reporting or corrective actions until the next scheduled reporting period if the exceedance triggers an immediate notification requirement under the permit. This is a direct violation of permit conditions and federal/state regulations, demonstrating a lack of diligence and potentially allowing pollution to continue unabated. Professional decision-making in such situations requires a systematic process. First, accurately interpret the monitoring data against the NPDES permit's effluent limitations and reporting requirements. Second, immediately consult the NPDES permit for specific actions required for the observed parameter and level. Third, implement any necessary operational adjustments to bring the parameter back within compliance. Fourth, follow the permit's specific notification and reporting protocols for any exceedances or violations. This structured approach ensures that all regulatory obligations are met, environmental protection is prioritized, and the plant operates within legal and ethical boundaries. Question 7. Research into the operational challenges at a wastewater treatment plant reveals a consistent increase in effluent turbidity and a decrease in secondary clarifier efficiency during periods of heavy rainfall. Concurrently, during dry periods, the plant experiences fluctuating influent pH levels and occasional spikes in specific organic compounds not typically found in domestic sewage. Considering the impact of different wastewater sources on treatment processes, which approach best addresses these observed operational issues to ensure compliance with discharge permits? Option A. Conduct a detailed investigation into the sources of infiltration and inflow to reduce their volume, and work with local industries to ensure effective pretreatment of their wastewater discharges. Option B. Focus solely on optimizing the biological nutrient removal processes, assuming the observed issues are temporary fluctuations in domestic wastewater strength. Option C. Implement increased chemical coagulant dosing in the primary clarifier and adjust aeration rates in the activated sludge process based on overall influent flow. Option D. Increase the sludge wasting rate to remove more solids from the secondary clarifier and implement a routine backwashing schedule for all filtration units. The correct answer is C. Implement increased chemical coagulant dosing in the primary clarifier and adjust aeration rates in the activated sludge process based on overall influent flow. Explanation: this scenario presents a common challenge for wastewater treatment plant operators, optimizing treatment processes in the face of variable influent characteristics. The challenge lies in understanding how different wastewater sources contribute to these variations and how those contributions impact the effectiveness of treatment stages. Operators must make informed decisions to maintain compliance with discharge permits and protect public health and the environment. This requires a deep understanding of the physical, chemical, and biological processes involved in wastewater treatment and how they respond to changes in influent loading and composition. The correct approach involves a comprehensive understanding of how domestic, industrial, and infiltration/inflow (I/I) sources uniquely affect treatment processes. Domestic wastewater typically contributes high organic loads and nutrients. Industrial wastewater can introduce a wide range of pollutants, including toxic substances, heavy metals, and high or low pH, which can disrupt biological treatment. Infiltration and inflow, while not introducing pollutants directly, increase the volume of water entering the plant, potentially reducing the efficiency of primary and secondary treatment by decreasing detention times and diluting influent concentrations. An operator who can identify the dominant source impacting a specific treatment unit and adjust operational parameters accordingly, e.g., aeration rates, sludge wasting, chemical dosing, is employing best professional practice. This aligns with regulatory requirements to operate the plant effectively to meet effluent standards, as mandated by regulations such as the Clean Water Act in the United States, which requires the attainment of secondary treatment standards and compliance with specific permit limits. Ethical considerations also demand proactive management to prevent environmental damage and protect public health. An incorrect approach would be to treat all influent variations as uniform. For instance, assuming that increased flow due solely to I/I requires the same operational adjustments as an increase in organic load from a new industrial discharge is a critical failure. This would lead to suboptimal treatment, potentially causing permit violations. Another incorrect approach is to focus solely on one type of source, without considering the synergistic or antagonistic effects of others. For example, only addressing industrial pretreatment without managing I/I could still lead to hydraulic overloading and reduced treatment efficiency. Failing to recognize the distinct impacts of each source means an operator cannot tailor process adjustments effectively, leading to inefficient operation and potential noncompliance with discharge permits, which is a direct violation of regulatory frameworks. Professional decision-making in such situations requires a systematic approach. First, continuously monitor influent characteristics, flow, BOD, COD, TSS, pH, specific industrial pollutants if known. Second, understand the design and operational capabilities of each treatment unit. Third, correlate observed influent variations with specific source types, e.g., high flow during rain events suggests I/I, sudden spikes in specific chemicals point to industrial discharge. Consistent high BOD/TSS suggests increased domestic or specific industrial contributions. Fourth, implement targeted operational adjustments based on the identified source and its impact on the affected treatment process. Finally, document all observations, adjustments, and their outcomes for continuous improvement and regulatory reporting. Question 8. To address the challenge of ensuring the long-term health of local waterways and the safety of downstream communities, a wastewater treatment plant operator is reviewing the facility's operational priorities. Which of the following approaches best reflects the core objectives of wastewater treatment as mandated by regulatory frameworks focused on public health and environmental protection? Option A. Implementing treatment processes that consistently achieve effluent quality significantly better than minimum permit requirements, even if it incurs slightly higher operational costs, to proactively safeguard aquatic life and human health. Option B. Prioritizing cost reduction strategies by reducing chemical dosages and operational staff hours, provided the facility remains technically within permit limits. Option C. Focusing solely on meeting the minimum numerical discharge limits specified in the facility's operating permit, as this is the primary legal obligation. Option D. Continuing to operate the plant using established historical procedures, assuming they have been adequate in the past, without actively seeking out new treatment technologies or regulatory updates. The correct answer is A. Implementing treatment processes that consistently achieve effluent quality significantly better than minimum permit requirements, even if it incurs slightly higher operational costs, to proactively safeguard aquatic life and human health. Explanation. The scenario presents a common challenge for wastewater treatment plant operators, balancing operational efficiency with the overarching regulatory mandate to protect public health and the environment. This requires a deep understanding of the goals of wastewater treatment beyond simply meeting discharge limits. Operators are stewards of public health and environmental integrity, and their decisions have direct consequences. The challenge lies in interpreting and applying regulatory objectives in practical, day-to-day operations, especially when faced with competing demands or resource constraints. The correct approach prioritizes the fundamental objectives of wastewater treatment as defined by regulatory frameworks. This involves understanding that meeting permit limits is a minimum requirement, but the ultimate goal is to prevent the transmission of disease and safeguard aquatic ecosystems. This approach aligns with the core principles of public health protection and environmental stewardship embedded in all wastewater treatment regulations. Specifically, it recognizes that effective treatment processes are designed to remove pathogens, reduce oxygen-demanding substances, and eliminate toxic pollutants to levels that do not harm human health or the environment. An incorrect approach that focuses solely on meeting minimum permit discharge limits fails to grasp the broader public health and environmental protection objectives. While permit compliance is essential, it is a means to an end, not the ultimate goal. Regulations are designed to achieve specific environmental and health outcomes, and a narrow focus on compliance without understanding the underlying purpose can lead to situations where the environment or public health is still at risk, even if technically within permit parameters. For example, a permit might allow for a certain level of nutrient discharge, but the broader objective is to prevent eutrophication of receiving waters, which could be harmed even if the discharge is technically compliant. Another incorrect approach that prioritizes cost savings above all else is ethically and regulatorily unsound. While fiscal responsibility is important, it cannot supersede the primary responsibility to protect public health and the environment. Cutting corners on treatment processes or maintenance to save money can lead to non-compliance, environmental damage, and potential public health crises, resulting in significant fines, legal action, and reputational damage. Regulations are in place to ensure a baseline level of protection, and compromising this for financial gain is a direct violation of the operator's professional and legal obligations. A third incorrect approach that relies on historical operational practices without considering current regulatory expectations or scientific advancements is also problematic. Wastewater treatment is a dynamic field, and regulations evolve based on new scientific understanding and emerging environmental concerns. Sticking to outdated practices can lead to suboptimal treatment performance, potential noncompliance with updated regulations, and a failure to adequately protect public health and the environment. Professional operators must stay informed about current best practices and regulatory updates. The professional decision-making process for operators should begin with a thorough understanding of the specific regulatory framework governing their facility, including the stated objectives of wastewater treatment. This understanding should then be applied to all operational decisions, prioritizing actions that best achieve the goals of public health protection and environmental safeguarding. When faced with competing priorities, operators must always err on the side of caution and ensure that their actions do not compromise these fundamental objectives. Continuous learning, adherence to best practices, and open communication with regulatory agencies are crucial for effective and responsible wastewater treatment operations. Question 9. Analysis of an unexpected surge in influent BOD and suspended solids at a wastewater treatment plant. What is the most appropriate initial step for the certified operator to take to ensure continued compliance with discharge permit limits? Option A. Make operational adjustments based on prior experience with similar influent fluctuations. Option B. Implement changes based on informal advice received from a senior operator regarding potential process modifications. Option C. Rely solely on the equipment manufacturer's troubleshooting guide for the primary treatment units. Option D. Immediately consult the facility's approved operations and maintenance (O&M) manual and relevant state/federal regulations for guidance on handling influent variations. The correct answer is D. Immediately consult the facility's approved operations and maintenance (O&M) manual and relevant state/federal regulations for guidance on handling influent variations. Explanation. Scenario analysis. This scenario presents a common challenge for wastewater treatment plant operators, balancing operational efficiency with strict regulatory compliance when faced with unexpected influent characteristics. The challenge lies in the potential for non-compliance if treatment processes are not adequately adjusted, which can lead to environmental damage and significant penalties. Operators must exercise sound judgment, relying on their understanding of treatment fundamentals and regulatory requirements to make informed decisions under pressure. Correct approach analysis. The correct approach involves immediately consulting the facility's approved operations and maintenance (O&M) manual and relevant state/federal regulations (e.g., EPA guidelines under the Clean Water Act for the U.S. This manual, developed and approved by regulatory agencies, outlines specific procedures for handling variations in influent, including troubleshooting steps and emergency protocols. Regulatory frameworks mandate that operators manage their facilities in a manner that consistently meets discharge permit limits. Therefore, referencing these authoritative documents ensures that any adjustments made are documented, justifiable, and aligned with established compliance strategies. This proactive and documented approach is crucial for demonstrating due diligence and maintaining permit compliance. Incorrect approaches analysis. Making adjustments based solely on past experience without consulting the O&M manual or current regulations is a significant regulatory failure. While experience is valuable, it cannot supersede documented, approved procedures. This approach risks deviating from established best practices and potentially violating permit conditions, as past conditions or regulatory interpretations may have changed. Implementing changes based on informal advice from a colleague, even a senior one, without verification through official documentation, is also a regulatory and ethical failure. This bypasses the established chain of command and the formal approval process for operational changes, potentially leading to unapproved modifications that could jeopardize compliance. Relying on manufacturers' recommendations for equipment alone, without cross-referencing with the facility's O&M manual and regulatory requirements, is insufficient. Manufacturer recommendations are often general and may not account for the specific operational context or the unique regulatory obligations of the facility. This can lead to operational decisions that, while perhaps technically sound for the equipment, do not ensure overall plant compliance. Professional reasoning. When faced with unexpected influent conditions, a wastewater treatment plant operator should follow a systematic, documented process. This involves 1. Recognizing the deviation from normal operating parameters. 2. Immediately consulting the facility's approved O&M manual for guidance on handling such variations. 3. Reviewing current discharge permit limits and relevant regulatory requirements. 4. Implementing adjustments as outlined in the O&M manual, ensuring all actions are recorded. 5. monitoring treatment process performance closely to confirm effectiveness and continued compliance. 6. Communicating any significant deviations or necessary major adjustments to supervisory personnel and regulatory agencies as required. This structured approach ensures that decisions are based on established protocols, regulatory mandates, and are fully defensible. Question 10. The investigation demonstrates that the primary clarifiers are experiencing a significant increase in settled solids, leading to a higher sludge volume being pumped. The operator needs to manage this increased primary sludge volume and ensure its proper disposal in accordance with all applicable regulations. Which of the following actions best represent the appropriate response for a certified wastewater treatment plant operator? Option A. Transport the thickened primary sludge to the nearest general municipal landfill for disposal. Option B. Discharge the thickened primary sludge directly to the receiving water body to alleviate the immediate pressure on the clarifiers. Option C. Investigate the upstream processes contributing to the increased solids loading, analyze the characteristics of the thickened primary sludge, and select a disposal method that complies with the facility's NPDES permit and relevant sludge management regulations. Option D. Immediately increase the sludge pumping frequency from the primary clarifiers to remove the excess solids and continue with the current disposal method. Correct answer is D. Immediately increase the sludge pumping frequency from the primary clarifiers to remove the excess solids and continue with the current disposal method. Explanation. Scenario analysis. This scenario is professionally challenging because it requires the operator to interpret and apply regulatory requirements for primary sludge handling and disposal in the context of observed operational issues. The challenge lies in identifying the root cause of the increased solids loading and selecting a disposal method that is both environmentally compliant and operationally feasible, avoiding potential permit violations and public health risks. Careful judgment is required to balance immediate operational needs with long-term regulatory compliance and environmental protection. Correct approach analysis. The correct approach involves a thorough investigation of the upstream processes contributing to the increased solids loading in the primary clarifiers. This includes reviewing influent characteristics, operational parameters of upstream units, e.g., grit removal, screening, and any recent process changes. Once the cause is identified, the operator must then evaluate disposal options for the thickened primary sludge that align with the facility's National Pollutant Discharge Elimination System, NPDES, permit requirements, and any applicable state or local regulations regarding sludge management. This might involve dewatering to meet specific solids content requirements for land application, incineration, or disposal at permitted landfill, ensuring that the chosen method minimizes environmental impact and regulatory noncompliance. This approach is correct because it prioritizes understanding the problem's origin and then selecting a compliant and sustainable solution, directly addressing the regulatory framework governing wastewater treatment and sludge disposal. Incorrect approaches analysis. One incorrect approach would be to immediately increase the sludge pumping frequency from the primary clarifiers without investigating the cause of the increased solids. This is incorrect because it fails to address the underlying issue, potentially leading to operational inefficiencies, increased energy consumption, and continued or exacerbated problems. Furthermore, it bypasses the critical step of assessing the characteristics of the sludge being removed and whether the current disposal method is appropriate for the altered sludge volume and composition, risking exceeding disposal capacity or violating permit conditions related to sludge handling. Another incorrect approach would be to discharge the thickened primary sludge directly to a receiving water body without proper treatment or dewatering. This is a severe regulatory and ethical failure. It directly violates NPDES permit conditions, which mandate specific treatment levels for wastewater and prohibit the discharge of untreated or inadequately treated sludge. Such an action would pose significant environmental risks, including oxygen depletion, habitat destruction, and contamination of the aquatic ecosystem, and would likely result in substantial fines and legal repercussions. A third incorrect approach would be to dispose of the thickened primary sludge at a landfill not permitted to accept such waste. This is a regulatory failure because landfill acceptance criteria are specific and designed to prevent environmental contamination. Disposing of wastewater sludge in a non-permitted landfill can lead to groundwater contamination, leachate issues, and violation of hazardous waste regulations if the sludge contains regulated substances. It also circumvents established protocols for responsible sludge management, which often involve specific pretreatment or stabilization requirements before landfilling. Professional reasoning. Professionals should employ a systematic problem-solving approach. First, they must identify and understand the problem by gathering data and investigating its root cause. Second, they must consult and strictly adhere to the facility's permits and all applicable regulations governing wastewater treatment and sludge management. Third, they should evaluate potential solutions based on their technical feasibility, environmental impact, and regulatory compliance. Finally, they must document their findings, actions, and decisions thoroughly. This framework ensures that operational decisions are informed, responsible, and legally sound. Question 11. During the evaluation of aeration system performance in a wastewater treatment plant, an operator observes that dissolved oxygen levels are consistently at the lower end of the acceptable range, and energy consumption for aeration is high. To address this, which of the following approaches would best align with optimizing oxygen transfer efficiency and ensuring regulatory compliance? Option A. Conduct a systematic evaluation of the oxygen transfer efficiency of both the diffused air and mechanical aeration systems under current operating conditions, considering factors like submergence depth, mixing patterns, and water temperature, to identify specific areas for improvement. Option B. Assume that the mechanical aerators are inherently less efficient than the diffused air system and deactivate them to reduce overall energy consumption. Option C. Focus solely on reducing the overall aeration time without measuring the impact on dissolved oxygen levels or effluent quality. Option D. Increase the airflow rate to the diffused aeration system and the motor speed of the mechanical aerators without further investigation. The correct answer is D. Increase the airflow rate to the diffused aeration system and the motor speed of the mechanical aerators without further investigation. Explanation. The scenario presents a common challenge for wastewater treatment plant operators: optimizing aeration system performance to meet effluent quality standards while managing energy costs. This requires a nuanced understanding of how different aeration methods impact dissolved oxygen levels and overall treatment efficiency, all within the bounds of regulatory compliance. The challenge lies in balancing operational effectiveness with economic considerations and adherence to permit limits. The correct approach involves systematically assessing the oxygen transfer efficiency, O, of both diffused air and mechanical aerators under current operating conditions. This includes considering factors like submergence depth, airflow rates for diffused systems, impeller speed and configuration for mechanical systems, and water temperature. By understanding the OTE of each system, an operator can identify which system is performing optimally and where improvements can be made. This aligns with regulatory requirements to maintain effluent quality as stipulated by the Clean Water Act, or equivalent jurisdiction's primary environmental legislation, and associated National Pollutant Discharge Elimination System, NPDES permits, or equivalent. Furthermore, optimizing OTE directly contributes to energy efficiency, a key operational goal that, while not always explicitly mandated by regulation, is a core principle of responsible plant management and often indirectly encouraged through performance-based incentives or cost-saving initiatives. An incorrect approach would be to solely focus on increasing airflow or motor speed without a thorough understanding of OTE. This could lead to over-aeration, wasting energy and potentially disrupting biological processes without a proportional increase in oxygen transfer. Another incorrect approach would be to assume that one type of aerator is inherently superior to the other without site-specific data. OTE is highly dependent on the specific design and operating conditions of the equipment and the wastewater characteristics. Relying on anecdotal evidence or manufacturers' general claims without verification can lead to suboptimal performance and noncompliance. Finally, ignoring the impact of operational parameters like temperature or mixing on OTE would be a failure to apply sound engineering principles and could result in inefficient operation and potential permit violations. Professional decision-making in such situations requires a data-driven approach. Operators should first consult their facility's operating permits and any relevant state or federal guidelines for effluent limits and operational best practices. They should then gather performance data on their existing aeration systems, including dissolved oxygen levels, energy consumption, and effluent quality. This data should be analyzed to determine the OTE of each system. Based on this analysis, operators can then implement targeted adjustments or investigate upgrades, always prioritizing methods that demonstrably improve OTE and contribute to meeting regulatory requirements and operational goals. Question 12. Market research demonstrates that trickling filter performance can be influenced by various factors. An operator notices a consistent, albeit slight, increase in effluent turbidity over the past week, coinciding with a minor increase in influent BOD. The plant's NPDES permit has a specific turbidity limit. Which of the following actions best reflects a proactive and compliant approach to this situation? Option A. Immediately increase the backwash frequency of the trickling filter media to dislodge any accumulated solids. Option B. Conduct a thorough investigation into the cause of the increased effluent turbidity, examining influent characteristics, filter media condition, and recent operational adjustments, while cross-referencing with permit requirements. Option C. Continue routine monitoring and document the trend. As the turbidity increase is currently within permit limits and the influent BOD increase is minor. Option D. Adjust the plant's overall treatment process by adding a coagulant to the influent to preemptively address the rising turbidity. Correct answer is C. Continue routine monitoring and document the trend, as the turbidity increase is currently within permit limits and the influent BOD increase is minor. Explanation. This scenario presents a professional challenge because it requires an operator to interpret subtle operational changes in a trickling filter system and link them to potential regulatory compliance issues without direct, immediate evidence of a violation. The challenge lies in proactive problem identification and intervention based on observed performance indicators, rather than reacting to a confirmed permit exceedance. Careful judgment is required to balance operational efficiency with environmental protection and regulatory adherence. The correct approach involves a systematic investigation of the observed changes in filter performance, specifically focusing on factors that directly impact effluent quality and could lead to a permit violation. This includes examining influent characteristics, filter media condition, and effluent monitoring data. This approach is justified by the regulatory framework's emphasis on preventing pollution and maintaining compliance. Proactive monitoring and investigation align with the operator's ethical responsibility to protect public health and the environment, and the legal obligation to operate the treatment plant in accordance with its permit. Early identification and correction of issues prevent potential permit violations, associated fines, and negative environmental impacts. An incorrect approach would be to ignore the observed changes, assuming they are within acceptable operational variability. This fails to meet the regulatory requirement for diligent operation and monitoring. It also represents an ethical failure to act responsibly in safeguarding the environment. Another incorrect approach would be to immediately adjust chemical dosages without understanding the root cause of the performance change. This could lead to overtreatment, increased operational costs, and potentially create new operational problems or even mask the underlying issue, thus delaying proper corrective action and potentially leading to a violation. Finally, an approach that involves only reacting to confirmed permit violations rather than investigating potential issues demonstrates a lack of proactive management and a failure to uphold the operator's duty of care. Professionals should employ a decision-making framework that prioritizes understanding the system's behavior. This involves 1. Observing and documenting all relevant operational parameters. 2. Correlating these observations with expected performance based on design and historical data. 3. Investigating potential causes for deviations, considering both operational and influent factors. 4. Consulting regulatory requirements and permit limits to assess potential compliance risks. And 5. Implementing corrective actions based on a thorough understanding of the root cause, with ongoing monitoring to confirm effectiveness. Question 13. Quality control measures reveal consistently elevated levels of both ammonia and nitrate in the final effluent, exceeding permit limits. The plant utilizes a conventional activated sludge process with a dedicated nitrification/denitrification stage. What is the most appropriate initial course of action for the wastewater treatment plant operator? Option A. Reduce the sludge wasting rate to increase the overall mixed liquor suspended solids concentration. Option B. Continue monitoring effluent quality for another 24 hours to see if the trend reverses naturally. Option C. Immediately increase aeration rates throughout the entire activated sludge system to promote nitrification. Option D. Systematically evaluate dissolved oxygen levels, pH, alkalinity, and sludge age in the nitrification stage, and assess carbonaceous BOD availability and anoxic conditions in the denitrification stage. The correct answer is D. Systematically evaluate dissolved oxygen levels, pH, alkalinity, and sludge age in the nitrification stage, and assess carbonaceous BOD availability and anoxic conditions in the denitrification stage. Explanation. Scenario analysis. This scenario presents a common challenge in wastewater treatment, maintaining optimal nitrification and denitrification processes under fluctuating influent conditions. Professional challenge lies in accurately diagnosing the root cause of elevated effluent ammonia and nitrate levels, and implementing the correct corrective actions without compromising overall treatment plant performance or violating discharge permit limits. Operators must possess a deep understanding of the biological processes involved, the impact of operational parameters, and the relevant regulatory requirements for nitrogen discharge. Failure to act decisively and correctly can lead to permit violations, environmental damage, and potential fines. Correct approach analysis. The correct approach involves a systematic investigation of operational parameters directly influencing nitrification and denitrification. This includes verifying adequate dissolved oxygen (DO) levels for nitrification, ensuring sufficient alkalinity and pH for nitrifying bacteria, and confirming adequate sludge age, or SRT, to support the slow-growing nitrifiers. For denitrification, it requires checking for sufficient carbonaceous BOD for heterotrophic bacteria, ensuring anoxic conditions, and verifying sufficient nitrate availability. By focusing on these critical biological and operational factors, the operator addresses the most probable causes of the observed nitrogen excursions. This aligns with the fundamental principles of biological wastewater treatment and the operator's responsibility to maintain process stability and compliance with discharge standards, as mandated by regulations like the Clean Water Act, assuming U.S. jurisdiction for this exam. Incorrect approaches analysis. Increasing aeration solely to address elevated ammonia without considering the impact on denitrification is an incorrect approach. A higher DO can enhance nitrification. It can also inhibit denitrification by consuming the limited carbon source and potentially leading to anoxic conditions being less achievable in the denitrification zone. This could worsen the overall nitrogen removal, reducing sludge wasting without a clear understanding of the sludge age and its impact on nitrifier populations is also incorrect. If the sludge age is already too low, reducing wasting further could lead to washout of nitrifying bacteria, exacerbating the ammonia problem. Conversely, if the sludge age is too high, reducing wasting might be appropriate, but it's not the primary diagnostic step for elevated ammonia and nitrate. Discharging effluent without further investigation, assuming the issue is temporary, is a direct violation of the operator's duty to monitor and control treatment processes to meet permit limits. This passive approach risks continued non-compliance and environmental harm. Professional reasoning. Professionals should employ a systematic troubleshooting framework. First, clearly define the problem: elevated effluent ammonia and nitrate. Second, gather data: DO, pH, alkalinity, SRT, effluent data, influent data. Third, hypothesize potential causes based on process knowledge and data. Fourth, test hypotheses by adjusting operational parameters or conducting further tests. Fifth, implement the most likely corrective action, monitor its effectiveness, and adjust as needed. This iterative process ensures that interventions are targeted, effective, and compliant with regulatory requirements. Question 14. Comparative studies suggest that while conventional activated sludge, extended aeration, sequencing batch reactors, SBR, and oxidation ditches all serve to remove organic pollutants, their efficacy in meeting stringent nutrient removal requirements and adapting to highly variable influent loads differs significantly. Considering a wastewater treatment plant facing increasingly strict effluent limits for nitrogen and phosphorus and experiencing significant diurnal fluctuations in flow and organic loading, which process variation is most likely to represent the optimal choice for reliable compliance and operational flexibility? Option A. Conventional activated sludge systems, as they are widely understood and typically require less complex operational control, making them a robust choice for consistent effluent quality regardless of influent variability. Option B. Oxidation ditches, which offer a continuous flow-through system with good BOD removal and can be configured for nutrient removal, but may be less adaptable to rapid changes in influent characteristics compared to other advanced configurations. Option C. Extended aeration, which provides a longer hydraulic retention time and sludge age, ensuring a high degree of organic matter stabilization and making it less susceptible to shock loads. Option D. Sequencing batch reactors, SBR, due to their inherent ability to operate in different phases, anoxic, aerobic, within a single tank, allowing for controlled nitrification and denitrification, and their flexibility in adjusting cycle times to accommodate variable influent conditions. The correct answer is D. Sequencing batch reactors, SBR, due to their inherent ability to operate in different phases, anoxic, aerobic, within a single tank, allowing for controlled nitrification and denitrification, and their flexibility in adjusting cycle times to accommodate variable influent conditions. Explanation: this scenario presents a common challenge for wastewater treatment plant operators, selecting the most appropriate process variation for a given set of influent characteristics and effluent discharge requirements. The challenge lies in understanding the nuanced performance of each system under varying conditions and aligning that performance with regulatory mandates and operational efficiency. A deep understanding of the underlying biological and physical principles of each process, coupled with knowledge of applicable regulations, is crucial for making an informed decision that ensures compliance and protects public health and the environment. The correct approach involves a thorough evaluation of the specific influent characteristics, e.g., BOD, COD, nitrogen levels, flow variability, and the stringent effluent quality standards mandated by the relevant regulatory body. This evaluation should then be matched against the known strengths and weaknesses of each process variation in achieving those standards. For instance, if the influent has highly variable organic loads and the discharge limits for nitrogen are strict, a sequencing batch reactor, SBR, might be favored due to its flexibility in managing fluctuating loads and its ability to achieve enhanced nutrient removal through controlled anoxic and aerobic phases. This approach is ethically sound and professionally responsible as it prioritizes compliance with environmental regulations, which are designed to safeguard public health and aquatic ecosystems. It also demonstrates a commitment to operational efficiency by selecting a process that can reliably meet discharge permits under anticipated conditions. An incorrect approach would be to select a process based solely on historical operational familiarity or perceived lower capital cost, without a rigorous assessment of its suitability for the specific influent and effluent requirements. For example, choosing a conventional activated sludge system simply because it is familiar, even if the influent is characterized by significant diurnal flow variations and high nutrient loads that a conventional system struggles to consistently treat to permit limits, would be a regulatory failure. This would likely lead to noncompliance with discharge permits, potentially resulting in fines, enforcement actions, and environmental damage. Another incorrect approach would be to prioritize a process that offers the lowest energy consumption without verifying its capacity to meet effluent standards. While energy efficiency is a desirable operational goal, it must be secondary to regulatory compliance. Failing to meet permit limits due to an inappropriate process selection is a direct violation of environmental laws and ethical obligations. Professional decision-making in such situations requires a systematic, data-driven approach. Operators should begin by thoroughly understanding the influent characteristics and the precise effluent discharge limits. They should then consult reliable technical literature and operational data on the performance of different process variations under similar conditions. A critical step is to engage with regulatory agencies to clarify any ambiguities in permit requirements and to discuss potential process upgrades or selections. Finally, a cost-benefit analysis that includes not only capital and operational costs, but also the probability of achieving consistent compliance and the potential costs of non-compliance should guide the final decision. Question 15. The control framework reveals that a wastewater treatment plant has received a new shipment of coagulants and flocculants. To expedite their integration into the treatment process, the operator is considering several options for their immediate placement and handling. Which of the following represents the most compliant and safest approach for managing these chemicals upon arrival? Option A. Store the chemicals in their original shipping containers without further inspection or segregation, and rely on visual checks for any signs of leakage. Option B. Store all incoming chemicals in a designated, well-ventilated area, ensuring each chemical is clearly labeled and segregated from incompatible materials, with appropriate PPE readily available for handling. Option C. Place all incoming chemicals together in the nearest available storage space, regardless of compatibility. To minimize handling time, Option D. Utilize general-purpose gloves and eye protection for all handling tasks, assuming these are sufficient for any chemical encountered. Correct answer is B. Store all incoming chemicals in a designated, well-ventilated area, ensuring each chemical is clearly labeled and segregated from incompatible materials, with appropriate PPE readily available for handling. Explanation. The control framework reveals a common operational challenge in wastewater treatment, ensuring the safe and effective handling of coagulants and flocculants. This scenario is professionally challenging because improper chemical storage and handling can lead to significant environmental contamination, worker safety hazards, and compromised treatment efficacy, all of which have direct regulatory implications. Operators must exercise careful judgment to balance operational efficiency with strict adherence to safety and environmental protection standards. The correct approach involves implementing a robust chemical inventory management system that prioritizes segregation of incompatible chemicals, ensures adequate ventilation in storage areas, and mandates the use of appropriate personal protective equipment, PPE, during handling. This approach is right because it directly addresses the potential risks associated with these chemicals. Regulatory frameworks, such as those governing hazardous materials and wastewater discharge, mandate specific protocols for chemical storage and handling to prevent spills, leaks, and worker exposure. Proper segregation prevents dangerous reactions, ventilation mitigates inhalation risks, and PPE protects operators from direct contact. Adherence to these practices ensures compliance with environmental protection laws and worker safety regulation, safeguarding both the environment and the workforce. An incorrect approach of storing all chemicals together in a single, poorly ventilated area without regard for compatibility poses a severe regulatory and ethical failure. This practice violates regulations concerning the storage of hazardous materials, which often require segregation of incompatible substances to prevent fires, explosions, or the release of toxic fumes. It also creates an unacceptable risk to worker safety, potentially leading to violations of occupational health and safety standards. Another incorrect approach of relying solely on visual inspection for leaks and spills, without implementing secondary containment measures or regular integrity testing of storage tanks and piping, is also professionally unacceptable. This failure to implement preventative measures directly contravenes regulatory requirements for spill prevention and control plans, which are essential for protecting water bodies and soil from contamination. It demonstrates a lack of due diligence in managing chemical risks. Finally, an incorrect approach of using generic, nonspecific PPE that is not rated for the specific chemicals being handled is a critical failure. Regulations mandate that PPE must be appropriate for the hazard. Using inadequate PPE exposes operators to significant health risks and violates occupational safety standards, potentially leading to serious injury or long-term health issues. Professional decision-making in such situations requires a systematic approach. First, identify all chemicals used and their specific hazard classification. Second, consult the safety data sheets, SDS, for each chemical to understand compatibility, storage requirement, and recommended PPE. Third, design and implement storage and handling procedures that align with regulatory mandates and best practices for chemical safety. Fourth, conduct regular training for all personnel involved in chemical handling and storage. Finally, establish a system for regular inspection and maintenance of storage facilities and equipment. Question 16. Investigation of a trickling filter system reveals a consistent increase in effluent ammonia concentrations and a slight turbidity increase over the past week. The operator observes that the influent flow rate has also increased significantly during this period, though the influent organic load BOD has remained relatively stable. Which of the following approaches best explains the likely cause of the observed performance degradation? Option A. The increase in effluent ammonia is a direct result of the influent BOD increasing, overwhelming the microbial community's ability to process organic matter. Option B. The stable organic loading indicates that the biofilm media itself has become inert and is no longer capable of supporting microbial activity. Option C. The increased hydraulic loading is likely causing excessive shearing of the established biofilm, leading to reduced nitrification capacity and subsequent ammonia breakthrough. Option D. The turbidity increase is solely due to the media breaking down into fine particles, which are then carried through to the effluent. The correct answer is C. The increased hydraulic loading is likely causing excessive shearing of the established biofilm, leading to reduced nitrification capacity and subsequent ammonia breakthrough. Explanation: this scenario presents a common challenge for wastewater treatment plant operators, diagnosing process upsets without relying solely on mathematical calculations. The challenge lies in interpreting observable process indicators and understanding the fundamental principles of biofilm media and loading parameters to identify the root cause of reduced effluent quality. Careful judgment is required to avoid misdiagnosis, which could lead to further process degradation, non-compliance with discharge permits, and potential environmental harm. The correct approach involves systematically evaluating the impact of hydraulic and organic loading on biofilm development within the media. This approach is right because it directly addresses the core process fundamentals relevant to media-based treatment systems. Understanding how increased hydraulic loading can scour biofilm and how excessive organic loading can lead to oxygen depletion and biofilm sloughing are critical to diagnosing performance issues. This aligns with the general principles of process control and optimization expected of certified operators, which are implicitly or explicitly covered in regulatory frameworks governing wastewater treatment operations. The ethical responsibility to maintain effluent quality and protect public health and the environment necessitates a thorough, principle-based investigation. An incorrect approach that focuses solely on visual inspection of the media without considering loading conditions fails to account for the dynamic nature of biofilm processes. Biofilm can appear healthy at a glance, but underlying loading issues can be causing detachment or inefficient treatment. This approach is ethically flawed as it neglects a comprehensive diagnostic process, potentially delaying corrective actions. Another incorrect approach that attributes the problem solely to media aging without investigating loading parameters overlooks the primary drivers of biofilm health and performance. While media can degrade over time, operational factors like hydraulic and organic loading are often the immediate cause of performance decline. This approach is professionally deficient because it prematurely concludes a cause without adequate investigation, potentially leading to unnecessary media replacement and continued effluent quality issues. A further incorrect approach that suggests adjusting chemical dosing without understanding the underlying cause of reduced treatment efficiency is also problematic. Chemical adjustments should be a consequence of a diagnosed problem, not a primary diagnostic tool. This approach risks masking the true issue, potentially leading to overdosing, increased operational costs, and unintended consequences for downstream processes or the receiving environment. Professional reasoning in such situations involves a structured, multifaceted investigation. Operators should first gather all available data, including influent and effluent quality, flow rates, and operational logs. They should then apply their knowledge of process fundamentals to hypothesize potential causes, considering the interplay between loading parameters and media performance. This hypothesis-driven approach, combined with targeted observations, and if necessary, further testing, allows for accurate diagnosis and effective corrective action, ensuring compliance and environmental protection. Question 17. Process analysis reveals a noticeable decrease in the efficiency of a trickling filter, characterized by increased odor and a decline in effluent quality. The operator suspects issues with the distributor arm, underdrain system, or ventilation. Which of the following diagnostic and corrective action sequences best adheres to standard operational protocols and regulatory expectations for wastewater treatment plant operation? Option A. Focus solely on adjusting the rotational speed of the distributor arm to compensate for any perceived imbalance, without investigating the underdrain or ventilation systems. Option B. Immediately initiate a high-pressure flush of the distributor arms and increase blower speed for ventilation, assuming mechanical blockage is the primary cause. Option C. Temporarily bypass the trickling filter to reduce the immediate load and allow for a more leisurely inspection of all components at a later date. Option D. Conduct a thorough visual inspection of the distributor arms for obstructions and wear. Check underdrain channels for clogging and structural integrity, and verify ventilation airflow rates against design specifications before implementing any corrective actions. The correct answer is B. Immediately initiate a high-pressure flush of the distributor arms and increase blower speed for ventilation, assuming mechanical blockage is the primary cause. Explanation: the scenario presents a common operational challenge in wastewater treatment plants, ensuring the effective functioning of distributor arms, under drains, and ventilation systems within trickling filters or similar biofilters. The professional challenge lies in diagnosing and rectifying issues that can lead to process inefficiency, effluent quality degradation, and potential permit violations. Accurate assessment requires a thorough understanding of how these components interact and the specific operational parameters and maintenance standards mandated by regulatory bodies. Failure to address these issues promptly and correctly can have significant environmental and financial consequences. The correct approach involves a systematic, evidence-based investigation that prioritizes safety and regulatory compliance. This approach begins with a visual inspection of the distributor arms for obstructions, wear, or imbalance, followed by an assessment of underdrain integrity to detect clogging or structural damage. Ventilation checks should confirm adequate airflow to support aerobic biological activity. This methodical process aligns with the general principles of good operation and maintenance, as outlined in typical wastewater operator certification frameworks, which emphasize proactive identification and resolution of mechanical and process issues to maintain optimal treatment performance and meet effluent standards. Regulatory guidelines often mandate regular inspections and maintenance schedules for all critical treatment components to ensure continuous compliance. An incorrect approach would be to immediately assume a single cause without thorough investigation. For instance, solely focusing on cleaning distributor arms without checking underdrain flow or ventilation would be a failure to conduct a comprehensive analysis. This could lead to misdiagnosis and ineffective repairs, potentially allowing underlying problems to worsen and leading to noncompliance with discharge permits. Another incorrect approach would be to bypass or disable a component, such as ventilation, temporarily alleviate a symptom without addressing the root cause. This is a direct violation of operational protocols and regulatory requirements, as it compromises the treatment process and can lead to process upset and permit violations. Neglecting to document findings and corrective actions, or failing to consult the plant's standard operating procedures and relevant regulations, also constitutes a significant professional and regulatory failure. Professional decision-making in such situations requires a structured approach. First, identify the observed operational anomaly. Second, consult relevant plant operating manuals and regulatory requirements. Third, conduct a systematic inspection and diagnostic process, prioritizing safety. Fourth, implement corrective actions based on the findings and regulatory guidance. And finally, document all actions and monitor performance to ensure the issue is resolved and prevent recurrence. Question 18. Benchmark analysis indicates a consistent decline in the plant's enhanced biological phosphorus removal (EBPR) performance, with effluent phosphorus concentrations trending upwards and approaching permit limits. The anaerobic zone appears to be functioning adequately in terms of detention time, and the aerobic zone maintains sufficient dissolved oxygen levels. Considering these initial observations, which of the following approaches represents the most prudent and effective course of action for the operator to diagnose and rectify the EBPR issue? Option A. Conduct a detailed analysis of the readily biodegradable organic matter (RBOM) and volatile fatty acid (VFA) concentrations in the influent to the anaerobic zone, and simultaneously assess the dissolved oxygen profile within the aerobic zone to confirm optimal conditions for phosphorus uptake by PAOs. Option B. Focus solely on increasing the return activated sludge (RAS) rate to improve the PAO population density in the aeration basins. Option C. Introduce chemical coagulants such as alum or ferric chloride into the secondary clarifier to chemically precipitate any remaining phosphorus before discharge. Option D. Immediately increase the aeration rate in the aerobic zone to ensure maximum phosphorus uptake, and implement a more aggressive sludge wasting strategy to reduce sludge age. The correct answer is A. Conduct a detailed analysis of the readily biodegradable organic matter RBOM and volatile fatty acid VFA concentrations in the influent to the anaerobic zone, and simultaneously assess the dissolved oxygen profile within the aerobic zone to confirm optimal conditions for phosphorus uptake by PAOs. Explanation: scenario analysis. This scenario presents a common challenge in wastewater treatment, maintaining optimal conditions for enhanced biological phosphorus removal (EBPR) while dealing with fluctuating influent characteristics. The professional challenge lies in accurately diagnosing the cause of EBPR failure and implementing the correct corrective actions without compromising overall plant performance or violating discharge permits. This requires a deep understanding of the biological processes involved, the interplay of operational parameters, and the relevant regulatory requirements for phosphorus discharge. Correct approach analysis. The correct approach involves a systematic investigation that prioritizes understanding the biological mechanisms of EBPR. This includes assessing the availability of readily biodegradable organic matter RBOM in the influent, which is crucial for the anaerobic stage of EBPR where phosphorus-accumulating organisms (PAO) release phosphorus to take up volatile fatty acids VFA. It also involves evaluating the dissolved oxygen (DO) levels in the aerobic zone, which are essential for PAOs to reuptake phosphorus. This approach is correct because it directly addresses the core biological requirements for EBPR as outlined in standard wastewater treatment principles and often referenced in regulatory guidance for nutrient removal. By focusing on the biological drivers, the operator can identify whether the issue stems from insufficient RBOM, inadequate anaerobic conditions, or suboptimal aerobic conditions, leading to targeted and effective solutions. This aligns with the ethical responsibility of an operator to manage the treatment process effectively and the regulatory obligation to meet phosphorus discharge limits. Incorrect approaches analysis. An approach that solely focuses on increasing aeration without first confirming a deficiency in the anaerobic stage or RBOM availability is incorrect. This could lead to excessive energy consumption and potentially disrupt the delicate balance required for EBPR, as too much oxygen can inhibit the anaerobic release of phosphorus. It fails to address the root cause if the problem lies upstream in the anaerobic zone or with influent characteristics. Another incorrect approach would be to immediately adjust sludge wasting rates without a thorough understanding of the PAO population dynamics. While sludge wasting is a critical operational parameter, making arbitrary changes without diagnosing the underlying biological issue can lead to either loss of PAOs or accumulation of non-PAO biomass, both of which would negatively impact EBPR. This approach bypasses the necessary biological assessment. Finally, an approach that involves adding chemical coagulants without a comprehensive biological investigation is also incorrect. While chemical addition can supplement biological phosphorus removal, it is typically a secondary strategy or used for polishing. Relying on chemicals as the primary solution without understanding why the biological system is failing is a failure to properly operate and maintain the biological treatment process, potentially masking underlying issues and leading to higher operational costs and chemical sludge generation. This approach neglects the fundamental biological principles of EBPR. Professional reasoning. When faced with a decline in EBPR performance, a wastewater treatment plant operator should adopt a systematic, biologically driven risk assessment approach. This involves 1. Confirming the problem. Verify the phosphorus removal deficiency through regular monitoring data. 2. Investigating the anaerobic zone. Assess the presence and availability of RBOM and VFAs, and ensure adequate anaerobic conditions for phosphorus release by PAOs. 3. Investigating the aerobic zone. Evaluate DO levels and their impact on phosphorus uptake by PAOs. 4. Assessing sludge characteristics. Examine PAO population and sludge age in relation to wasting rates. 5. Considering influent variability. Analyze any changes in influent flow, organic load, or nutrient concentration. Based on this comprehensive biological assessment, targeted operational adjustments or process modifications can be implemented. This methodical approach ensures that corrective actions are effective, cost-efficient, and compliant with environmental regulations. Question 19. The review process indicates that the grit removal system at the wastewater treatment plant is functioning effectively, but there is a need to reevaluate the current grit disposal practices to ensure full compliance with environmental regulations and best management principles. Considering the potential for contamination and the requirements of approved disposal facilities, which of the following approaches represents the most responsible and compliant method for grit disposal? Option A. Transporting the grit to a licensed landfill that has been verified to accept wastewater treatment plant grit, after ensuring the grit meets the landfill's specific acceptance criteria. Option B. Repurposing the grit for use as fill material in local construction projects without obtaining necessary testing and regulatory approval. Option C. Disposing of the grit at a general municipal landfill without prior confirmation of its acceptance policy for such waste. Option D. Storing the grit in large piles on the plant property for an extended period until a cost-effective disposal solution is identified. The correct answer is A. Transporting the grit to a licensed landfill that has been verified to accept wastewater treatment plant grit, after ensuring the grit meets the landfill's specific acceptance criteria. Explanation: this scenario presents a professional challenge because it requires an operator to balance operational efficiency with regulatory compliance and environmental protection when dealing with grit disposal. The challenge lies in ensuring that the chosen disposal method not only effectively removes grit from the treatment process, but also adheres to all applicable environmental regulations regarding landfill acceptance criteria and potential contamination. Careful judgment is required to select a method that is both practical for the plant's operations and environmentally responsible. The correct approach involves understanding and adhering to the specific requirements for grit disposal as mandated by the relevant Environmental Protection Agency, e.g., EPA in the U.S. This typically includes characterizing the grit to ensure it does not contain hazardous materials and disposing of it at an approved landfill or facility that can legally accept such waste. This approach is best professional practice because it directly aligns with regulatory mandates designed to prevent environmental pollution and protect public health. By following these guidelines, the operator ensures the plant operates within legal boundaries and minimizes its environmental footprint. An incorrect approach would be to dispose of grit at a municipal landfill without verifying if it meets the landfill's acceptance criteria for industrial or wastewater treatment byproducts. This is a regulatory failure because many landfills have specific restrictions on what they can accept, and wastewater grit may contain substances that require special handling or are prohibited. Ethically, this approach is unacceptable as it risks environmental contamination and potential harm to the public. Another incorrect approach would be to stockpile large quantities of grit on plant grounds indefinitely without a clear disposal plan or proper containment. This is a regulatory failure, as it likely violates waste management regulations that require timely disposal and proper storage of waste materials. It also poses an environmental risk due to potential runoff or leaching, and an ethical failure as it demonstrates a lack of diligence in managing plant byproducts responsibly. A third incorrect approach would be to attempt to reuse or repurpose the grit for unapproved applications, such as landscaping or construction fill, without proper testing and regulatory approval. This is a significant regulatory and ethical failure. It bypasses established waste management protocols and could lead to the introduction of contaminants into the environment or public spaces, potentially causing harm and violating regulations designed to prevent such occurrences. The professional decision-making process for similar situations should involve a thorough understanding of the plant's waste streams, the characteristics of the grit generated, and the specific regulatory requirements for its disposal. Operators should consult their facility's permits, local and state environmental regulations, and the acceptance criteria of potential disposal sites. When in doubt, seeking guidance from regulatory agencies or environmental consultants is a crucial step in ensuring compliance and responsible waste management. Question 20. The performance metrics show a consistent increase in effluent BOD and suspended solids over the past week, coinciding with a noticeable odor issue at the RBC facility. The influent flow rate has remained stable, but visual inspection of the RBC media reveals areas of thick, dark, and somewhat detached biofilm. Which of the following operational adjustments is the most appropriate initial response to address these performance issues? Option A. Implement a temporary reduction in influent flow to the RBC units to decrease the hydraulic and organic loading on the biofilm. Option B. Increase the rotational speed of the RBC discs to improve oxygen transfer and biofilm health. Option C. Increase the dissolved oxygen levels in the aeration basins upstream of the RBCs. Option D. Begin a routine chemical cleaning of the RBC media to remove excess biofilm. The correct answer is B. Increase the rotational speed of the RBC discs to improve oxygen transfer and biofilm health. Explanation. This scenario presents a common challenge for wastewater treatment plant operators, interpreting performance data from a rotating biological contactor (RBC) system and identifying the root cause of declining effluent quality. The challenge lies in distinguishing between issues related to biofilm development, hydraulic loading, and organic loading, all of which can impact RBC performance. Professional judgment is required to avoid misdiagnosing the problem, which could lead to ineffective operational adjustments, further deterioration of effluent quality, and potential regulatory noncompliance. The correct approach involves a systematic evaluation of the RBC system's operational parameters in conjunction with the observed performance metrics. This includes assessing the physical condition of the RBC media, e.g., biofilm thickness, sloughing, reviewing influent flow rates and hydraulic loading, and examining the influent organic load, e.g., BOD-COD. By correlating these factors, an operator can pinpoint the most probable cause of the performance decline. For instance, if effluent BOD is increasing and there is evidence of excessive biofilm sloughing, it suggests an organic overload or insufficient media surface area for the applied load, leading to the need for process adjustments like flow reduction or increased media cleaning. Regulatory compliance, as outlined in insert-specific U.S. EPA or relevant state environmental agency regulations, e.g., 40 CFR Part 133 for secondary treatment standards, or state-specific NPDES permit requirements, mandates that operators maintain effluent quality within permitted limits. Therefore, a data-driven, diagnostic approach is essential to ensure compliance and protect receiving waters. An incorrect approach would be to immediately assume a single cause without thorough investigation. For example, solely focusing on increasing the rotational speed of the RBC discs without considering the biofilm condition or organic load could exacerbate sloughing and worsen effluent quality, violating the principle of responsible operation and potentially leading to permit violations. Another incorrect approach would be to adjust chemical dosing without understanding the underlying biological process deficiency, which is an inefficient use of resources and unlikely to resolve the core issue, thus failing to meet the operational diligence expected of a certified operator. Furthermore, ignoring the hydraulic loading and attributing the problem solely to biofilm development might lead to operational changes that do not address potential hydraulic bottlenecks, which can also impair RBC performance by reducing contact time and oxygen transfer. These missteps represent a failure to apply sound engineering principles and adhere to the professional responsibility of maintaining effective wastewater treatment. Professional decision-making in such situations requires a structured diagnostic process. Operators should first review all available performance data, including influent characteristics, effluent quality, and operational parameters of the RBC unit. They should then form hypotheses about potential causes, prioritizing those that are most consistent with the observed data and known RBC behavior. Next, they should gather additional information or conduct specific tests to confirm or refute these hypotheses. Finally, based on the confirmed cause, they should implement appropriate operational adjustments or maintenance procedures, documenting all actions taken and their rationale. This systematic approach ensures that interventions are targeted, effective, and in line with regulatory requirements and best operational practices.